want to look at two more specific Dalton's Law style problems that are a little bit more complicated than just simple addition. This first problem is what I would call a chart problem, and it tends to have constant conditions, and that gives you a very specific way forward with the problem. Under constant conditions, we're usually looking at more of a perv-nert style problem, so we can use PV equals nRT. So let's take a look at what this problem looks like, and then I'll explain how we make this chart. So a sample of hydrogen gas is collected over water at 32 degrees Celsius. The volume of the gas collected is 0.20 liters. The partial pressure of the water vapor at 32 degrees Celsius is 0.12 atm. The pressure of the atmosphere is 1.07 atm. What is the partial pressure of the hydrogen gas and how many moles were collected? So you can see, I'm even getting tripped up just reading the problem. There's so many words here. I'm having trouble kind of deciphering what's the problem giving me and any path forward to how we're going to get to what the problem even wants. So I usually organize all of my information into a chart. Now what I notice here is that absolutely nothing in this problem indicates in any way, shape, or form that the conditions are changing. And that does tell me I can probably organize my information into a chart. Now I like to make sure that that chart includes a couple pieces of information. First of all, I want to monitor absolutely everything there is to know about a gas. I can measure quite a few things about a gas. I can measure its pressure, its temperature, the moles, and the volume. So I'm going to organize that in kind of a special way. And if you'll notice, that already looks like a PV equals nRT style problem. It's just that R is missing. Across the top of my chart, I like to organize my data for all of the different types of gases that are in this problem. Now there were two that were mentioned, hydrogen and water, but I also like to make a column for total because that can be a little different. So here is my hydrogen, my water, and my total. And now it's simply a matter of unpacking the data that's on the inside of the problem and into my chart. Before I do that, let me just explain how I feel about this chart. This chart to me is a lot like a puzzle. And one of my favorite types of puzzles to do is a Sudoku puzzle. And just like Sudoku, this chart has its rules. And we just need to make sure that we're following them so that we can get to the final answer. Rule number 1. Vertically, up and down in any single column. If you have 3 out of the 4 variables, you can find the 4th by doing a PV equals nRT problem. Quick plug and chug, and in and out, and you should have your number. Well, horizontally, going across the rows, there's also a couple different rules. 2 of the variables you can straight fill across, as they will not change from one column to the next. Volume and temperature should absolutely always be constant since we're not changing any of the conditions. The remaining 2 columns are subject to Dalton's law of partial pressures. So not only will the total pressure add up to equal that total column, but so will the moles. And that just simply makes sense that, if I have moles of one thing and moles of another, that if I want to know total moles, I would add them. So these 2 columns would add up to equal the total. So now let's start to lace in our information. Firstly, I see that we're dealing with a temperature of 32 Celsius. We hate Celsius. Let's immediately convert that into Kelvin. And I see that that's about 305 Kelvin. Now it's in one of the rows that I should straight fill across. So I'm going to simply layer 305 into every single temperature box that I would have present. The next number that I see is 0.20 liters. And just like the temperature, that should be straight filled across because the volume of the container is the volume of the container. It will not change from one gas to the next. So that all should be 0.2 liters. Next, I see that the partial pressure, and that just belongs to the water vapor at that temperature, is 0.12 atm. I'm going to fill that in for the pressure of the water. Next, I see that the pressure of the atmosphere is equal to 1.07 atm. That I'm going to put into the total pressure. And then finally, we get into what the problem is actually asking us for. And it asks is for the partial pressure of the hydrogen And I'm going to indicate that on my chart by kind of shading in or giving a circle or highlighting that box in some way so that I know when I have that answer, I've kind of answered my problem. But then the problem asks for a second thing. It asks for how many moles of that gas were also collected. So I'm going to highlight both the pressure and the moles box so that I know once I've provided answers in those two things, I'm done. I'm good with my problem. And here's where the puzzling part of this problem begins. No two of these chart problems are going to be the same. You're going to have to use some of your problem-solving strategies to kind of get from point A to point B. So here's what I see with this problem. Instantly, I notice that going straight across, I'm missing only one pressure that I've been provided with the other two. And if I remember correctly, the pressures of both gases on the inside of the container should add up to equal my total. So I can use a little algebra and solve now for the pressure of the hydrogen. So if I take 0.12 out of my total of 1.07, I should see what's left over. It ends up equaling 0.95 atm. So great. Now without very much trouble, I've actually found one of the two numbers that I needed in the problem. Part 2, I got to fill in that last box. And with this part, I notice that I have 3 out of the 4 variables needed for a perv-nert problem, a PV equals nRT. So now I'm going to plug and chug that information into PV equals nRT. So here is my problem all plugged and chugged in, and I'm just going to calculate that final answer for my number of moles. And in this case, I found that it actually equaled 0.0076 moles for my gas and hydrogen. I can plug that into my chart, and at this point, I'm finished with my problem. So I'm hoping that you can see that if you can identify that under constant conditions, there's absolutely nothing that's changed here. You can organize your information into a chart, and it should help auto-solve this problem for you by playing a game of chemistry Sudoku. Unfortunately, in every problem, we're not always going to be dealing with constant conditions and a mixture of gases. Sometimes we're going to be dealing with changing conditions, and that brings us to example problem number 2.